students, this problem comes under module 1 conduction. Okay, that is a slab problem. Okay, consider a large plane wall of a thickness 0.2 meter. Thermal conductivity is 1.2 watt per meter degree Celsius, and surface area is 15 meter square. The two sides of the wall is maintained at 120 degrees Celsius and 50 degrees Celsius. Okay, determine the variation of temperature within the wall and the value of temperature at distance x is equals to 0.1 meter. Okay, so and next part of the question is find the rate of heat conduction through the wall under steady condition. Okay, so here the given data are length is given, that is a 0.2 meter, and the temperature initial temperature is 120 degrees Celsius and the T2 final temperature is 50 degrees Celsius, right? So and thermal conductivity is given, that is 1.2 watt per meter degree Celsius, right? And area is 15 meter square. Here we have to find temperature at a distance x is equals to 0.1 meter. Okay, and the rate of heat conduction, okay, q, that is q. Okay, so go to page number one second, go to page number 44. Okay, this temperature distribution formula is available, okay, at page number 44, that is a Tx minus T1 divided by T2 minus T1, which is equals to x by L. Okay, so here only unknown term is T, temperature at a distance x. Okay, x here is 0.1 meter. Okay, so we have to find Tx. Okay, T at a distance of 0.1 meter. So interchanging, you will get 0.1 divided by 0.2 into 50 minus 120 plus 120. So the temperature at a distance x becomes 85 degree Celsius. Okay, so the next part of the problem is we have to find rate of heat conduction, right? That is q. Q for conduction is formula is K A into T1 minus T2 divided by L, right? So Q becomes 1.2 into area is 15. Okay, in the bracket Ti is T1 is 120 and T2 is 50 divided by length is 0.2. So you will get 6300 watts. Okay, this is first problem of conduction unit. Okay, and the second problem, surface is having a area of 1.2 meter square and maintained at a temperature of 300 degrees Celsius, exchanges the heat by radiation. Okay, here radiation type of problem. Okay, with another surface at 40 degrees Celsius, the emissivity is 0.2 epsilon. Okay, so determine the heat loss by radiation, and the second one is the value of thermal resistance, and the third one is for the same rate of heat transfer, find the value of equivalent convection coefficient. Okay, here we have to find Q radiation, R thermal resistance, right? R thermal. So and next one is H, that is heat transfer coefficient. So the given data are area is given, that is 1.2 meter square, and temperature T1 is given, that is T100. T2 is 40 degrees Celsius, epsilon is given, emissivity that is 0.52. Okay, for this problem, this is a radiation type of the problem, right? So according to Stephen Boltzmann law, Q radiation is equals to sigma into A into epsilon into Ts raised to 4 minus T infinity raised to 4, right? This is the formula, right? So here we have to convert all the temperatures, that is in degrees Celsius. So here we have to convert it into Kelvin. Okay, so 300 plus 273, Ts becomes 573 degrees Celsius, sorry, Kelvin, and T infinity becomes 313 Kelvin. Okay, substitute both the temperatures. So sigma value is 5.67 into 10 raised to minus 8. Area is given, that is 1.5, and epsilon is also given, that is 0.52, and Ts is 573 raised to 4 minus 313 raised to 4. So Q radiation you will get 4343 watts. Okay, 0.08 watts. So next part of the problem is we have to find thermal resistance, right? So Q is equals to delta T by R theoretical, right? So here we have to find R theoretical. So T1 minus T2 divided by Q radiation. So T1 is 573 and T2 is 313 divided by Q value is 4343.08. So thermal resistance you will get 0.059 degrees Celsius per watt. Okay, so next part of the problem is here we have to find Q, not Q, H, heat transfer coefficient H. Okay, so Q is known, area is known, delta T is known, right? So only the unknown part is H. So Q is 4343.08, which is equals to H into 1.5 into 573 minus 313, right? So H will get 11.13 watt per meter square degree Celsius. Okay, this is the problem of this problem is about radiation. Okay, and the third problem is surface at 250 degrees Celsius is exposed to a surrounding at 110 degrees Celsius. It convects and radiates to the surrounding. Okay, the convection coefficient and radiation factor are 75 watt per meter degree Celsius and unity respectively. Okay, if the heat is conducted to the surface through a solid having a thermal conductivity 10 watt per meter degree Celsius. Okay, what is the thermal gradient at the surface of the solid? Okay, here we have to find thermal gradient, that is dt by dx. Okay, so the given data are thermal conductivity is given, that is 10 watt per meter degree Celsius. Surface temperature is given, that is 250, converted into Kelvin, that is 523 Kelvin. So T infinity is 110 degrees Celsius, 383 Kelvin. So emissivity epsilon is given, that is 1, and heat transfer coefficient H is 75. So here you have to find dt by dx, right? So the only the way is, so Q conduction, which is equals to Q convection plus radiation, right? So for a Q convection conduction, the formula is minus K into dt by dx, right? Which is equals to, for Q convection, for convection HA into Ts minus T infinity, and for radiation Stephen Boltzmann law, that is a sigma into epsilon into A into Ts raised to 4 minus T infinity raised to 4. Here area get cancelled. So dt by dx is equals to 75 into 250 minus 110 plus 5.67 into 10 raised to minus 8 into emissivity is 1, okay, into 523 raised to 4 minus 384, 83 raised to 4. Okay, the bracket 1 divided by 10, right? 10, K value is 10, so 1 divided by 10. Okay, that is T sign. So dt by dx becomes 1300 minus of 1352.21 degree Celsius per meter. Okay, this is about the conduction problem. Thank you.